This research presents a novel class of exact solutions for the non-equilibrium expansion of a scalar field in 1+1 dimensions, with homogeneity in the transverse plane. By relaxing symmetry constraints, including no boost invariance and axis reflection invariance, and local equilibrium initial conditions, the study provides a more comprehensive understanding of quantum corrections in dynamical situations. The Wigner distribution for a free scalar field is discussed, highlighting the expectation of off-shell contributions in non-equilibrium scenarios. The general class of solutions for the 1+1 dimensional expansion is explored, and the semi-classical limit is presented, accompanied by numerical comparisons. These findings demonstrate non-trivial vacuum effects, even for a free scalar theory, and significant deviations from classical free streaming that persist in the long-time limit. Building upon previous studies on quantum corrections at global and local equilibrium, this research contributes to the understanding of quantum effects in heavian collisions. The study employs natural units, where h equals c equals k underscore b equals 1, and adopts the mostly minus convention for the Minkowski metric. Key mathematical concepts, including tree vectors represented by bold letters and the D'Alembert operator denoted by a box, micro, are utilized to derive the solutions. The right minus left derivative, denoted as f x, left right arrow micro g x, equals f x micro g x micro f x g x, is also employed in the analysis. The results of this study aim to bridge the gap between complex quantum field theories and simpler classical descriptions, providing a deeper understanding of the physics involved in high-energy collisions. The off-shell Wigner distribution provides a novel approach to computing expectation values of the stress-energy tensor T micro nu with reduced knowledge of the system. Given a density matrix, ρ, the exact expectation value of T micro nu can be computed via equation 1. But this process becomes impractical for complex configurations. The Wigner distribution W, x, k, derived from the density matrix, offers a more accessible method for obtaining T micro nu and the conserved current J micro, as seen in equations 3 and 4 for a free charged field. This method can be generalized to a free uncharged scalar field, yielding the expectation value of T micro nu, as given by equation 5. Notably, full knowledge of the state ρ is not required to compute T micro nu or J micro. The Wigner distribution provides a sufficient tool. However, additional knowledge of the system is necessary to investigate aspects such as energy fluctuations. The Wigner distribution satisfies a set of equations of motion derived from the Klein-Gordon equation, which can be represented in compact form as equation 6 for both charged and uncharged fields. Restoring Planck's constant and the speed of light c yields equation 7, which can be decomposed into its real and imaginary components, resulting in the two separate equations 8. These equations express the second-order partial differential equation of W, x, k, and its condition for translational invariance. The Wigner distribution's inherent reality allows for this decomposition, providing a powerful tool for analyzing the stress-energy tensor and conserved current. This approach enables the computation of expectation values with reduced knowledge of the system, making it a valuable method for studying complex configurations. Neglecting the second-order term in the expansion of the Wigner distribution, the first equation in 8 simplifies to the on-shell condition, approximating W as proportional to delta k squared m squared. The second equation in 8 mirrors the collisionless Boltzmann equation without approximation. This suggests that, by retaining only the lowest-order terms in the expansion, one can recover classical free streaming from the full solutions of the Wigner distribution. In addition to the classical limit, there exists a class of trivial on-shell solutions, namely, spacetime translation invariant ones, where partial differential mu W equals 0 everywhere. The first equation in 8 implies the on-shell condition for translation invariant states, regardless of the action scale or any expansion. The second equation is fulfilled due to the symmetry constraints alone. Most solutions of interest, however, are either trivial or off-shell. For example, consider a Wigner distribution W, x, k, equals delta, k squared m squared, 1, x, k, equals delta k squared m squared integral d to the power of 4 xi 2 pi squared eix xi 1 xi k, where 1 x k is a generic Fourier transformable on shell function. The exact equations 8 then imply that k xi 1 xi k equals 0 and xi squared 1 xi k equals 0, meaning both k mu and xm must be on shell vectors. K squared equals m squared and xi squared equals 0, and they must be orthogonal. However, non-vanishing light-like and time-like vectors are never orthogonal, and a solution proportional to delta to the power of 4 xi fulfills both equations, which is trivial. Since off-shell Wigner distributions are common, it is crucial to find non-trivial exact solutions to understand the extent of quantum corrections to classical free streaming. The paper then proceeds to consider a 1+1 dimensional expansion, where a general classification of the solutions of equations 8 is beyond the scope of the present work. Many times, if the full 3+1 dimensional case is beyond reach, it is convenient to insert symmetries that reduce the effective dimensions. In the context of Heavian collisions, the Bjorken symmetry and its generalization are of particular interest. The authors choose to start with the Bjorken symmetry, which includes invariance under rotation and translations in the transverse plane, under longitudinal boosts, and under axis reflection in the longitudinal direction. Surprisingly, it is simpler to find the form of the solutions for a smaller symmetry group, and it is always possible to implement additional symmetries later. In this section, the authors consider only the ISO 2 part of the full Bjorken symmetry, the homogeneity in the transverse plane. The invariance of the density matrix R with respect to an element of the Poincaré group constrains the Wigner distribution in a specific way, which is discussed further. The authors derive the properties of the Wigner distribution under translations and Lorentz transformations, starting with its definition in equation 13. They demonstrate that translations in the transverse plane do not affect the integration variables, leading to the invariance condition in equation 14. For Lorentz transformations, the Wigner distribution must satisfy equation 15, implying that W x k equals W lambda x lambda k. Combining these results, the authors conclude that the Wigner distribution has the form W x k equals W t z k kt kz, where kt equals square root kx squared plus ky squared, and depends only on the modulus kt, but not on the direction in the transverse plane. The authors then solve the second equation in 8, using the method of characteristics, obtaining a class of solutions Wf zkt kz k kt kz. They generalize this solution to include distribution-valued solutions, arriving at the most general solution W t z k kt kz equals Wr zkt kz k kt kz plus delta k delta kz wd t z kt. Finally, the authors introduce the notation W equals zkt kz and V equals tkz kz, which will be used later in the derivation. The first equation in 8 is then rewritten in terms of the regular part Wr. In quantum field theory, the Wigner distribution W t z k0 kt kz is a fundamental concept. To derive its general solution, the authors start by solving the equation for W r, the second derivative of Wr with respect to W. This yields a cosine and sine function solution in terms of Fevin and Fod, respectively. To ensure a smooth transition when the radical becomes imaginary, which is possible for k2 less than 0, the sine function is modified. Next, the authors solve the Klein-Gordon equation for Wd, a two-dimensional scalar field with mass equal to the transverse mass, mt. The general solution for Wd involves an integral over the variable xi, with a xi, kt, and a asterisk operator, xi, kt, as coefficients. The final expression for the Wigner distribution, W t z k0 kt kz, is obtained by summing the solutions for Wd and Wr. Interestingly, This expression does not resemble classical free-streaming solutions. The first term is spacelike, k2 less than 0, and does not correspond to anything in the classical limit, while the last two terms can be timelike but do not resemble classical solutions. The authors note that classical solutions may still be a reasonable approximation of quantum free streaming in 1+1 dimensions, as will be demonstrated in the next section. To facilitate this discussion, they introduce a dimensionless quantity chi, which enables a compact rewriting of the general solution, setting the stage for the examination of the semi-classical limit. The Wigner distribution, W, T, Z, K0, Kz, is expressed as the Fourier transform of the field correlation function, A, xi, kt, and its complex conjugate, as given in equation 25. This expression is then rewritten in terms of the Planck constant, h, and the speed of light, c, in equation 26. Notably, the authors caution against applying the Riemann-Lebesgue lemma to the oscillating integral in the first term, as this would lead to an incorrect conclusion that the stress-energy tensor and current vanish in the classical limit. Instead, the authors emphasize the importance of considering the explicit H factors in the definition of the Wigner distribution and the physical dimensions of the fields. The classical counterparts of the stress-energy tensor and current are given in equation 27, with the limits holding if the quantum Wigner distribution fulfills the condition in equation 28. The focus is on the particle contribution to the Wigner distribution, W plus x, k, defined in equation 29, where only the timelike part of W has a chance to be on shell in the limit. The authors acknowledge that neither W plus nor W is guaranteed to have an exclusively on shell limit, and that states with limited particle numbers and high entanglement may exhibit non-trivial quantum behavior. However, they aim to find a class of solutions with recognizable on-shell limits, and begin by rewriting the particle contribution of equation 26 in the form of equation 30. Throughout this section, the importance of considering the Planck constant and the physical dimensions of the fields in the definition of the Wigner distribution and its classical counterparts is highlighted. The prefactor in equation 30 plays a crucial role in obtaining the correct limit, particularly when considering the factor a 2 pi, Planck over 2 pi 1, which bears resemblance to the definition in equation 2, with an added action scale in the numerator to ensure Febin and Fod are dimensionless. To extract the free streaming limit, certain assumptions are made, specifically operating within the forward light cone, where t greater than z. This region is particularly relevant in heavian collisions, where the collision typically occurs at t equals z equals 0. In this spacetime region, theta, k0, theta, k2 square meters c2, is equivalent to theta, v, theta, k2 square meters c2. By employing variables v and w in the integration measure, equation 31 expresses d4k as d2k tdv tau 2 for t greater than z, where tau represents the spacetime proper time. Equation 32 relates chi2 to v2w2, and a change of variables is applied, resulting in equation 33. The Jacobian of the transformation is partially compensated by the prefactor in equation 30. In the forward light cone, equation 34 reveals that the right-hand side of equation 30 resembles the classical, on-shell, Lorentz covariant measure in momentum space for chi equals 0, as seen in relativistic kinetic theory in Milne coordinates. Further analysis in equation 35 demonstrates that if the right-hand side of equation 30 becomes proportional to delta chi in the small Planck over 2 pi 1 limit, classical on-shell integrals are recovered. To investigate which classes of F provide the delta chi in the proper classical limit, a generalization of the epsilon-dependent delta family is introduced in equation 36. This delta family approaches the Dirac delta function as epsilon approaches 0. The results of the change of variables and the structure of the right-hand side of equation 30 in the forward light cone are displayed in equations 33 and 34, respectively. These findings provide a crucial step towards understanding the relationship between the classical limit and the properties of F. We establish the limiting behavior of certain integrals as epsilon approaches 0, assuming the uniform convergence of the integrals of d x with the test functions. For a function with a double dependence on x and other parameters p1, the limiting behavior can be extended as lim epsilon right pointing arrow 0 integral dx epsilon g x epsilon x p1 psi x equals psi 0 integral di g y 0 p1, where psi x is a generic test function. Considering functions Fevin and Fod of the form, and calling epsilon equals h 2 pi a w equals with a, we have the limiting behavior. Lim epsilon right pointing arrow 0 plus theta chi theta 2 minus chi 2 pi cos w chi epsilon Fevin chi epsilon k0 kt kz equals 1/2 delta chi integral d chi 2 pi cos w chi Fevin chi square root m2t plus kz 2 kt kz, and lim epsilon right pointing arrow 0 plus theta chi theta 2 minus chi 2 pi sin w chi epsilon Fod chi epsilon k0 kt kz equals 1/2 delta chi integral d chi 2 pi sin w chi Fod chi square root m2t plus kz 2 kt kz. These right-hand sides essentially represent a Dirac delta and a counter Fourier transform. To select a class of functions that yield the classical free streaming limit, we can define Fevin as the real part of a Fourier transform in W equals with A, depending only on the even part in W left right arrow minus sign W, and Fod as the imaginary part, depending only on the odd W left right arrow minus sign W part, of the classical distribution function f. Fevin, chi epsilon, kt, kz, equals 2 re integral dw, 2 pi, f, w, kt, kz, e minus u, chi epsilon and Fod, chi epsilon, kt, kz, equals 2 im integral dw, 2 pi, f, w, kt, kz, e minus u, chi epsilon. Using this class of functions in equation 30, the momentum integrals of W plus become integral d4 kW plus equals integral 2 d chi 2 pi h cubed integral d2 kt dw square root 4 chi caret 2 square meters t tau 2 plus w2 cos w chi h Fevin plus sin w chi h Fod a 2 pi h equals integral 2 d chi 2 pi h cubed integral d2 kt dw square root 4 chi caret 2 square meters t tau 2 plus w2 cos w chi epsilon Fevin plus sin w chi epsilon Fod 1/2 pi. In the small epsilon limit, i.e., large action scale of the system in h units, we recover the classical free streaming limit by construction for f. Lim epsilon right pointing arrow 0 integral d4 kW plus equals 1, 2 pi h cubed integral d2 kt dw square root m2 t tau 2 plus w2 f w kt kz equals 1, 2 pi h cubed integral d2 kt dw square root m2 t tau 2 plus w2 f wa kt kz. The solutions obtained from equation 41 can be extended in two ways. Firstly, considering multiple action scales A, where A is the smallest non-vanishing scale and A equals Ra, with R being the ratios of the action scales. This leads to the extended forms of f and f in equation 44. The classical free streaming function f w underscore a k underscore t k underscore z r can be obtained by taking the epsilon right pointing arrow 0 limit, keeping the ratios r fixed. The second extension involves replacing the delta chi in equation 40 with chi right pointing arrow 0, allowing for the multiplication of f with a function h chi as long as h 0 equals 1. This leads to a large class of exact solutions that all converge to the same classical free-streaming solution in the small h limit. However, computing integrals like equation 42 is more complicated than the classical version, equation 43, due to the fast oscillations introduced by the trigonometric functions. A general prescription for estimating the difference between the full quantum solutions and their classical approximations is currently lacking, and a case-by-case analysis is required. An example relevant to Hebbian collisions is presented, considering the massless case and assuming longitudinal boost invariance and axis reflection invariance. The boost invariance implies that only boost invariant combinations of k and k_z can appear in F, while the axis invariance requires that only even functions of W are admitted. A Gaussian form for the asymptotic free-streaming distribution function, f, w, k_t, is chosen, given by equation 46, with the action scale A equals t tau. A modified form of the quantum precursor, f, is used, given by equation 47, which allows for simplification of the momentum integrals. The momentum integrals are then evaluated, resulting in equation 48, a modified form of equation 42. Figure 1 compares the integrands of equations 52 and 53 at proper time tau equals tau, illustrating the effects of varying epsilon values on the integrand. The classical result, epsilon right pointing arrow 0, is represented by the black solid line, while the green dotted, blue dashed, purple dot dashed, and red dashed lines correspond to epsilon values of 0.5, 0.7, 0.9, and 1, respectively. A change of variables is introduced, expressing t in terms of k squared and chi squared, and the integral is rewritten in terms of dimensionless variables w and y squared, yielding equation 49. This equation represents the integral over the transverse plane. The longitudinal pressure PL is defined as the z micro z nu component of the stress energy tensor T micro nu, expressed in equation 50 as an integral over k. Substituting the change of variables, equation 51 is derived, representing the longitudinal pressure in terms of the dimensionless variables. The chi and y integrations in equation 51 can be performed exactly. The inessential factor t to the power of 4, 2 pi, h, cubed to the power of 5 to the power of 5 to the power of 5, tau cubed can be removed, as it appears identically in the classical integral. This simplification facilitates a direct comparison between the classical and modified results. The comparison of integrands in Figure 1 highlights the significant effects of varying epsilon values on the integrand. The derived equations 49 and 51 provide a framework for further analysis of the longitudinal pressure in terms of dimensionless variables. The authors derive a complex integral equation, 52, that captures the quantum corrections to the classical stress-energy tensor, contrasting it with its classical counterpart, 53, obtained by taking the limit epsilon right pointing arrow 0. The oscillatory integrand of equation 52 exhibits large fluctuations for large action scales epsilon. A comparison of the integrands of equations 52 and 53 for varying epsilon values, as shown in Figure 1, reveals that for epsilon is less than or equal to 0.5, the integrands are nearly identical, while for larger epsilon, the quantum corrections become significant. Numerical computation of the integrated quantum corrections reveals they are relatively small, on the order of 1% or less, up to epsilon approximately equals 1. However, for larger epsilon, the quantum corrections become more substantial, reaching 20% for epsilon approximately equals 2 and 50% for epsilon is greater than or equal to 3. The authors suggest that kinetic theory can be a good approximation in the low-density limit for final states, but significant quantum corrections can occur in the very initial stages. The corrections are smaller for tau 0 and larger for tau much less than tau 0. The paper's main results include the exact solution of the Wigner distribution for a free scalar field, relaxation of the local equilibrium requirement, and computation of quantum corrections to the classical stress-energy tensor. The authors emphasize the importance of these corrections in the early stages of Hebbian collisions. The Wigner transform of the Green's functions can be solved using an immediate approach, following the prescription in Ref. 50. This method involves algebras similar to that of the Green's functions, where the Klein-Gordon operator applied to free fields yields a number instead of a distribution. The Wigner distribution can be expressed as a general equation, A1, applicable to both charged and uncharged fields, where kappa equals 1 for charged fields and kappa equals 0 for uncharged fields. This equation can be further transformed into equation A2 by multiplying it by ik x1 by 2 and integrating over d4k. Applying the Klein-Gordon operator with respect to x1 on the right-hand side of equation A2 results in equation A3, which equals 0. This leads to equation A4, where a counter Fourier transform is applied to obtain a Dirac delta function A5. Ultimately, this results in equation A6, representing the Wigner distribution in terms of its Fourier transform. In addition to the evolution equations, 8, the Wigner distribution is subject to other constraints. These include the requirement for positive eigenvalues of the normal-ordered Hamiltonian, the necessity for total energy to be positive, and less familiar constraints that can be proven. The definition of the Wigner distribution, too, and its relation to microscopic states can also provide additional information. Using the Peskin-Schroeder notation and normalization, B1, the Wigner distribution can be directly written in terms of the expectation value of creation and annihilation operators. The Wigner distribution, a fundamental component in quantum field theory, is defined by the equation W x k equals integral d caret 4 p d caret 4 q 2 pi caret 4 delta p squared m squared delta q caret 2 square meters delta x p plus q 2 delta k pq. This four-dimensional integral over momenta p and q involves the Dirac delta function, resulting in a simplified expression for W x k in terms of four delta functions. The first two terms of this expression contribute exclusively to the timelike part of W, specifically to the particle and antiparticle contributions, respectively. This is due to the Dirac deltas implying that p and q are on shell, positive energy vectors with the same mass. However, the condition for the first two terms to contribute is derived, showing that this condition is impossible to satisfy. The last two terms of the expression contribute only to the spacelike part of W. This has the significant implication that not all microscopic states provide a Wigner distribution with a spacelike part. The density matrix, pure or mixed, is defined as a sum over classical probabilities of physical states. When extended to an infinite number of possible physical states, the discrete sum becomes an integral with a probability density. It is noted that the expectation values of certain operators can be non-zero only if some of the states are in a quantum superposition between states differing exactly by one particle-antiparticle pair in particle content. In particular, if the states are eigenstates of either the particle number or the antiparticle number operator, these expectation values vanish. An intriguing consequence of the expression for W x k is that the on-shell part of the Wigner distribution is spacetime independent, and hence, the strictly on-shell Wigner distributions are trivial. This is demonstrated by analyzing the Dirac delta function in the expression for W x k. Building upon the derivations presented in preceding sections, specifically equation B3 and the discussion surrounding equation B8, this analysis demonstrates that the first delta in the right-hand side of equation B8 is compatible with the second delta exclusively when p equals q. This compatibility stems from the fact that when p equals q, the phase factor e caret I pq x that multiplies the delta function reduces to unity, effectively removing the spacetime dependence. Consequently, the delta functions become spatially invariant, allowing for a consistent mathematical formulation. The analogous formulas for the other Dirac delta functions can be obtained through similar reasoning, thereby establishing a comprehensive framework for analyzing the compatibility of delta functions in this context. Moreover, generalizing these results to the uncharged scalar field is straightforward, with the primary distinction being a division by 2 and the relation b_p equals a_p. This generalization underscores the versatility of the mathematical framework and its applicability to diverse physical systems. The compatibility of delta functions has significant implications for the analysis of quantum field theories, particularly in the context of particle interactions and scattering processes. By establishing a rigorous mathematical framework for understanding the behavior of delta functions, this analysis provides a foundation for further research into the intricacies of quantum field theories and their applications. Unfortunately, it seems like you forgot to include the content to refine. Please provide the text, and I'll transform it into a direct, concise form suitable for voiceover narration, following the guidelines you provided.